Let us now try to understand what this axiomatic approach to probability means. So from here on, we will try to develop methods in which we can numerically calculate the probability of an event from a given sample space, right? So let S be the sample space of a random experiment. So you're taking an experiment and S is basically its sample space. The probability P is a real valued function. So first of all, remember this probability P is a real valued function. You can't have complex numbers here. Whose domain is the power set of S. So your S, your sample space might have a lot of points. It might have a lot of outcomes. The power set of all outcomes. You can in this probability function, you can give input as a combination of any of those outcomes, right? So if A, B, C are outcomes which are possible, you can this probability function can have A comma B as its input. It can have just A as its input, or it can have A comma C as its input, right? Any combination. So basically its input is or its domain is basically the power set of S, right? It can't take anything. It can't take any case or anything which is outside S, right? It can only take values which are from S, or it is not values actually, cases which are from S. And its range is within the interval 0 to 1. So this is very, very important. Your probability always lies between 0 to 1. Whatever you put in as your input, the output that you get has to lie between 0 and 1, right? Now, this probability P must satisfy these axioms, these three axioms. So the first axiom is, for any event E, probability E is greater than or equal to 0. That's very evident here from this itself, that if your probability function is lying between 0 and 1, you take up any event E. So I might just choose this region. So I might choose this region from my sample space, and I'm calling this region as the event E, right? You can do that. Then probability of that is greater than or equal to 0. Probability can't be negative, right? It has to be greater than or equal to 0. Probability of the sample space is equal to 1. So if in my experiment I have A, B, C as my outcome, right, as the only outcomes possible, so these will make up the sample space, right? So the probability of sample space is 1. That means probability of anything happening from the sample space. So if I for example, if I toss a die and I 1, 2, 3, 4, 5, 6, right, that makes up my sample space. Now, if I say what is the probability of that sample space? Probability of sample space is 1, right? Because that will always happen. Anything from the sample space or any basically outcome from the sample space will always happen. So that is basically probability of sample space is equal to 1, because that is the complete case that fulfills your entire probability range, right? Nothing outside this can happen. So if there are 10 things possible, sample space means all those 10 things, right? So nothing is missing. That is what it means. So this probability of sample space is equal to 1. Now, if E and F are mutually exclusive events, then probability of E union F is equal to probability of E probability of F. So we'll be looking at this again when we look at the addition theorem, right? So for now I'll just explain it to you using a diagram. So this is my sample space. Now if I say E and F are mutually exclusive, I've already told you mutually exclusive means they don't have anything in common. This is your E, this is your F. Probability of E union F means either A or B, right? Either A or B. That means I'm talking either about this region or about this region, right? That means probability of E plus probability of F, because you simply have to add them and that will cover both these cases because they are mutually exclusive. But if they had something in common, right? If there was some region here in middle which was in common, then it would be a different thing that we will discuss later in detail, right? Now, from these three axioms, what can be followed is this thing, basically these results. So if your sample space is a combination of these events or these outcomes, or W1, W2, W3, so on up to Wn, if sample space consists of all this, then the first thing is probability of any of these. So for each omega, or Wi which belongs to S, which means you can have either W1 or W2 or Wn, anything, right? Probability of any of those events will lie between 0 and 1, right? So that is something that's evident here. Probability function P lies between 0 and 1. And here also, if you pick up any event, its probability will lie always between 0 and 1. 0 is basically that case where nothing from the sample space is happening, and 1 is that case where everything from the sample space is happening and everything else will lie between 0 and 1, right? Second thing is, if I add up the probabilities of all these cases, so then that will be equal to 1. So the fact here is omega W1, W2, W3, these things that you see here, they make up your entire sample space, right? So let's understand this using a diagram. So you might have W1, W2, W3, so on up to Wn, all these events, right? W1, W2, W3, so on up to Wn. Now, if I add their probabilities, if I add all their probabilities, that means I'm actually tracing the entire sample space, right? Because I'm adding all the events that are making up the sample space. So remember, for this to hold good, W1, W2, W3, so on up to Wn, all these should be your exhaustive events, right? So we've already seen what exhaustive events is. Nothing other than these n cases are possible, right? You can't have a Wn plus 1. That's not there, right? Only these are a part of your sample space. So if I add up their probabilities, that will make up the entire sample space, and the probability of sample space is 1, right? So that is why you have 1 as its result. Coming to 3, that is for any event A, probability of A is equals to addition of all those events which are a part of A. So for instance, if I take up this region which has only a W1, W2 and W3. So W1 is here, W2 is here, W3 is here. If I pick up only this region and I call this as A, then probability of A is probability of W1 plus probability of W2 plus probability of W3, right? Because W1, W2, W3, these W's belong to your A, which is basically this, right? So you pick up any region, all the W's which belong to that region, you have to add their probabilities, and that will be equal to your probability of that region. That I'm calling that region as A here, right? So this was what axiomatic approach to probability was. So now we have started to deal cases as numbers now. So all of this chapter is basically picking up cases which will be given in words, converting them to numbers, and using these axioms to get what is the probability of a particular event happening from a given set of events. That is what the chapter is all about, right? So with this, we complete this very, very important module called an axiomatic approach to probability. Let's now move on to the classical definition of probability.